The automation methodology for bus performance verification using the IP-XACT. Abstract. Bus fabric of modern SoC is becoming massive as number of DMAs, directory memory access is increasing. Thus, the bus performance verification is required to measure the performance of each master, which reflects the congestion of the bus fabric. However, the preparation of the verification needs huge amount of time and implies the possibility of human errors, as the bus performance test must be processed in a full chip level environment to stimulate the bus fabric, and large number of verification targets are distributed in the design. Here, we propose an automation methodology to reduce the TAT turnaround time of the bus performance verification by using IP-XACT as the metadata of design. With this methodology, we have experimentally demonstrated that over 90% of verification targets are automatically processed with TAT is reduced to 1 minute from 2 weeks. We expect to apply this methodology to all projects which require the bus performance verification. Introduction. The modern SoC is challenging to provide multiple features in a single system. To achieve this goal, SoC designers focus on integrating more application-specific hardware in the chip. In such circumstances, the number of the bus components, such as MMU, Memory Management Unit, SSO bus, arbitration logic, and asynchronous bridges increasingly as more DMA masters are implemented. In the aspect of each master, it's important to know how their performance is affected by bus component under that data path. However, estimating the impact is not straightforward. As a solution, a bus performance verification is introduced to measure the performance of all masters, while the bus components are influencing the bus as a performance metric and measures them at this pre-silicon level while all of the bus components are in operation. The bus performance verification is executed under the emulation environment because it requires a full chip level environment where all of the components are fully implemented without instruction. In addition, the test measures over a few gigabytes per second, which means that a cycle-based simulation is excessively time-consuming. Considering a large duty, design under test, and fast runtime, emulation environment suited for bus performance test. Approximately over 100 of masters are verification targets, so it is barely impossible to bring up each master. So in the aspect of the bus performance verification, internal algorithms of the master is not a verification target. Outgoing traffic is what the bus performance verification is focusing on. In such circumstances, the bus performance verification uses the TG traffic generator to replace each master. By using TG traffic generator, user can avoid the bring up of each master and can ensure the controllability of the test environment. So big figure 1 shows the TG replacement of the real trees masters in the SoC. So every master which is verification target is replaced by the TG for the test. Figure 1 is the TG replacement of verification target in SoC. Multi-layers of the components are abstracted as a single block. The problem of the bus performance verification is that the preparation of the TG replacements take a lot of time. So TG generates data transactions based on protocols like AXI or ACE. So all of the signals consisting of the protocol must be known to the TG. So TG database files is used to describe the design information, such as the signal hierarchy and a bit width of the signals. The TG database files is delivered to the emulating image buffer, which replaces the master to the TG based on the TG database file. So when we need multiple TGs in a single emulation image, we must write down the all signal information of every TG to the database file. For example, when a single TG uses 5 each signals and which write to 100 each of the TGs, then the database file should have the 5000 5,000 each signal information. If we manually process this job, it would be tedious and time-consuming. So in addition, manual work might cause any human errors. Errors in the TG database are not detected at emulating image build steps, and they are observed by inaccurate result while the test is performing. This study suggests the automation methodology for TG replacements to reduce verification TAT and human errors. This methodology applied IP-XACT to obtain the signal information. IP-XACT provides metadata of the design. Therefore, the various kind of verification methodology utilize IP-XACT for automation. In this methodology, IP-XACT plays a significant role because the DUT, design testing, is a large and full chip size SoC, which means that the parsing the data metadata requires less effort, while reading the whole RTL register transfer level code is much harder. Section 2 is the background. A. Bus performance verification. Recent SoCs are adding new features into their systems to meet the increased demand of the market. Typically, SoC is designed with cascaded bus components, each of which has a complex algorithms and configuration. When integrating the bus component into SoC, it is essential to ensure the masters connected to the bus component are served with their target minimum latency and bandwidth. This kind of verification is challenging in some points. First, to measure the performance of the masters, a huge amount of the data transaction is tested in which is above the few gigabytes per second. Second, the verification must be done under full chip level environment that all of the bus components are fully included in the test bench, which affects the test runtime. Third, the test must be done all of the masters in the SoC. Usually there are over 100 of masters in the SoC, so which makes the test bench complicated. In such a situation, the bus performance verification is established to measure the performance of each master. It uses the emulation environment and synthetic traffic patterns. Emulation environment is applied to obtain the fast runtime compared to the simulation environment. Emulation takes advantage of running large DUT and in measuring heavy traffic in timely manner. The synthetic traffic patterns are used for a convenient control of traffic patterns. TG is used to generate synthetic traffic patterns. By applying the TGs to all verification targets, the verification TAT can be reduced significantly. Figure 2 shows the concept of the bus performance verification. So the verification measures the performance metric of the data path from the master to memory interface. Yes, figure 2 is the concept of the bus performance verification. The verification measures the performance metric of the data path. So the information about the verification target is delivered through the bus specification. The bus specification contains information of each verification target, its property like clock frequency and minimum latency and bandwidth, and port hierarchy. B. Traffic generator. TG. The traffic generator is a component that can send a synthetic traffic instead of masters for the purpose of emulation-based verification. Figure 3 shows the diagram of TG that replaced the master. When a master is replaced by TG, a real master does not have to send any traffic, and the TG imitates the data traffic of the real master by driving the signals of the protocol. TG makes the verification much easier because the initiating master does not have to operate. Unlike its real master, TG does not require any vectors for the operation, can provide a convenient generation of the data transaction. This characteristic is much helpful when the multi-TGs are applied to the DUT, so because the user can save the bring-up time for each master. Figure 3. TG replaces the real master and starts the traffic instead of the master. To use the TG, two files are required. The first is the TG database file, which describes all signals required by the TG. Though the TG sends traffic based on a protocol such as AMBA, AXI, and ACE, the user must prepare all of the signals related to the protocol. The TG database file is delivered to the emulation image builder for the further step. The second is the TG configuration file, which determines the transaction property. The configuration can contain the target bandwidth, destination address range, the QoS value, and the chain hint. So the test bench reads the TG, the configuration file, while the test is running. Figure 4 shows the entire flow of the TG, including emulation and verification. The TG database file is used for emulation image and build, and the TG configuration file is used for test run. So the figure 4 is emulation-based verification using TG. Chapter 3 is a proposed approach. The methodology suggests the automatic generation of the TG database file and TG configuration file for the bus performance verification. Before this methodology was introduced, bus specification, bus architecture diagram, and RTL code were used for generate the database and configuration file. The user picks the verification target on the bus specification file and then manually searches the approximate location of the bus port of the bus architecture diagram. Finally, with the location found in the bus architecture diagram, user must search the precise architecture of the precise hierarchy of the verification target at RTL code. This step was time-consuming and inadequate for defining the huge amount of the TG information, which can easily cause human errors. The biggest problem of the manual work was ambiguous expression of the verification target on the bus specification and the bus architecture diagram. Bus specification did not define the full architecture hierarchy of the verification target, so they only mentioned the IP, intellectual property, name which the verification target is implemented. Also, the bus target diagram is a visual file, PSD file, which shows the simplified interconnected relationship of the IP inside the SoC. Moreover, the bus architecture diagram was drawn by the hand, which does not guarantee the latest status of the RTL code. So, the user must read and analyze the RTL code to get the exact hierarchy of the verification target. To solve this time-consuming and unreliable workflow, proposing methodology was invented. In the previous methodology, the bus specification only provided the IP name and the verification target is included. By now, it changed to provide a full hierarchy of the port. This little change was very helpful to increase the accuracy of automation result. So the next is to run the methodology to input files are required. For the first file is the bus specification file, which is the Excel format. The methodology reads the Excel file without additional processing. This feature is helpful when the errors are found in the file because the user can easily rerun the methodology file by simply editing the specification. So the second input file is the IP-XACT. As a result of this methodology, the TG database file and the TG configuration file is generated. TG database file requires a signal list from the IP-XACT and port hierarchy from the bus specification file. TG configuration file is generated by the traffic configuration requirement for example bandwidth, the burst size, and the length from the bus specification. So figure 5 shows a simplified diagram which explains the data input and output of our proposed methodology. The figure 5 input and output diagram of the methodology. The name of the methodology is auto_TG_mon. The methodology is composed of 3 steps: extract, a find intersection, and output generation. The figure 6 shows a more detailed diagram of the methodology. The extraction stage reads the input files and find intersection stage and compare the input data and both input files from both the input files. So when the result from the find intersection stage, the output generation stage create output files. Figure 6 is input and output diagram of the proposed methodology. At a certain stage, the bus specification and the IP-XACT are parsed with the class instance of the object-oriented programming language, which makes the methodology to be minimally modified even the format of the input is dramatically changed. The bus specification is delivered in the Excel format. Each row contains the information about the verification target, which is the IP name, the required bandwidth, and clock frequency. In this step, minor errors can be reported to the user, for example, empty or not a member in the Excel file. Moreover, depending on the property, exceptionally out-of-range values can be reported as an error. Table 1 shows an example of the bus specification file. So Table 1 is a simplified example and many other properties are contained in the actual table. ARVALID and AWVALID signal path is used as a representative for the port hierarchy. Cells marked in red will be reported as an error. As mass frequency of the modem TMA0 is reported as an error because 10 MHz for the clock frequency is exceptionally a small value. The other error cases are empty cells as not a number. Errors in the instruction stage can be ignored by user depending on the property of the verification target. For example, some master port can only provide a read feature. In this case, the write signals hierarchy has nothing to be written. Table 1, an example of the bus specification. See, at the find intersection stage, two data groups from the different inputs are compared with the other. The point of the comparison is signal hierarchy information. Since the bus specification only holds the ARVALID and AWVALID hierarchy, the only valid signals are compared with between the bus specification and the IP-XACT. Find intersection stage is required to find a verification target which is available for the automation. In the later stage of the methodology, ARVALID and AWVALID signal hierarchy from the bus specification is restored the full signal list containing AR address, AR ready, and many other signals in the protocol by using metadata extracted from the IP-XACT. Comparison results are arranged into three different cases. The verification target from the bus specification is found at IP-XACT. This case means that the verification target is available for the automation. 2. The verification target from the bus specification is not found at the IP-XACT. This case is an error with some possibility. The first possibility is that the IP designer does not use the IP-XACT. Unfortunately, there is nothing to do with the verification target. The other possibility is an error of the specification. By the fact that the specification is updated by hand, the error can happen. Whenever there are major updates in RTL code which changes the signal hierarchy, the bus specification is not guaranteed to reflect the RTL changes. Whereas IP-XACT are updated automatically, these errors in the bus specification are reported to the user. The last case is that the master port is found in the IP-XACT, but not found in the bus specification file. This method does not care about the case because these ports are not the verification target. The master port of the bus component corresponding to this case, for example MMU, as well as arbitration logic and CTC, clock domain crossing logic. So at the output generation stage, two output files are created. Signals list for the TG database files obtained from the IP-XACT. Traffic settings for the TG configuration files are parsed from the bus specification. So section 4 is experimental result. We applied this method to the test environment for the development. Test was done for the 190 of the masters in the design. The methodology successfully generated the alpha files within 1 minute. Also, the methodology got 22 errors, 8 were from the exact extraction stage, which is detected by reading the bus specification file. These errors on the bus specification can be fixed with the little effort. The 14 errors occur from the find intersection stage. These errors occur the verification target does not use the IP-XACT or the bus specification does not reflect the updated RTL. This requires the modification of the bus specification. After deliberation with the design team, the verification target can be changed according to the RTL update. After the test, we finally applied this methodology to the latest design of the mobile device. 155 each of the verification targets were chosen for the bus performance verification. By applying this methodology, the TG traffic generator database file, the TG computation file were generated within 1 minute, which was 2 weeks of work in the previous project. As a result, the bus performance verification was able to obtain the tested result in the early stage of the verification. Also, the bus performance test can find the 17 bugs as a workaround the bus specification changes target marked performance metric or the burst length of the clock frequency is adjusted to meet the performance requirement. Section 5 is conclusion and future works. We have successfully developed the methodology for this automatic generation of the TG traffic generator database file and the TG computation file for the performance verification. Also, this methodology was applied to the latest project, which reduced the TAT from 2 weeks to less than 1 minute. This result showed that this methodology successfully achieved the goal. Moreover, since TG database file and the TG computation file has no dependency with the performance verification, so this methodology can be applied to all verification items which uses the TG traffic generator. Okay. Today I read this paper, Automation Methodology for Bus Performance Verification using IP-XACT from the DVCON2023. Thank you for your time and see you next time.